by Iurii TIMROV. Again, as usual, post all your questions on Slack now, since we have many people that can answer there, and you will get an answer for sure. And for tutors, if you deem it necessary, you can invite participants to join breakout rooms to give more detailed, to give assistance about more technical issues. So please, Iurii, we proceed with the answer.
Thank you, Ivan, for the introduction. Hello to everybody. I'm from École Polytechnique Fédérale de Lausanne in Switzerland, and it's my great pleasure to be with you today or tonight. So the day 4, we have hands-on on advanced functionals. We have also 4 tutors available. So I just remind that you can ask questions in the breakout rooms for those who are in Zoom, and for those who are on YouTube, or you can post your questions as usual. All right, so let's get started. We will do 3 exercises. The first one is for iron oxide. You already saw this in the lecture just half an hour ago using DFT plus U method. Second example is DFT with hybrid functionals. We will see how this works for silicon. And the last example is using van der Waals functionals, and we see how this works for graphite. You can see the note below that these examples can be quite heavy. This is why we can use allocated clusters for this school. And for those who are on YouTube, they can run on the laptop or on the workstation, depends what you have. All right, so let's start with DFT plus U. A brief reminder from the lecture. As Professor De Gironcoli showed, in DFT plus U, we correct the total energy functional, such that we have the standard DFT expression, the DFT total energy, plus the Hubbard U corrective term. So I just want to explain that this corrective term, it's already the Hubbard contribution minus the so-called double counting term. So this is one final expression. And this Hubbard correction energy looks like this, where we have the effective Hubbard U parameter, because this is actually Hubbard U minus Un's exchange J. So we call it one effective Hubbard U in the simplified rotationally invariant formulation of DFT plus U. We have a Kronecker symbol, delta MM prime, where M and M prime are magnetic quantum numbers. Also, we see here object, which is N, which depends on indices I, sigma, MM prime. Index I corresponds to atoms, so it labels atoms. Sigma is the spin index. It can be spin up or spin down. And this object is called occupation matrix. It's defined as 2 scalar products. One is between Kohn-Sham wave function psi, which depends on spin, V, which is the electronic band index, and K is the K point. So scalar product between psi and phi, which are localized functions. This can be, for example, atomic-like functions, which are centered on atoms. And the same scalar product, complex conjugated, I'm sorry, not complex conjugated, but in different order, and also index M instead of M prime. And F, sigma, Vk are the electronic occupations, for example, Fermi-Dirac or anything else. Okay, and if we compute the trace of this occupation matrix, so we sum up over index M and spin, we obtain object which depends only on the atomic index I, and this is nothing but the number of electrons sitting on the shell that we are trying to correct. For example, if we're applying a Hubbard U correction to the d electrons, so d shell, or f electrons, f shell, so this number n of I will give us how many electrons are sitting on that shell. Finally, by knowing this expression for the energy, we can obtain the modified Kohn-Sham equation. It's written below by taking functional derivative of the energy with respect to the wave function. So we obtain this modified Kohn-Sham equation where the blue term is the standard DFT contributions, the kinetic energy plus the Kohn-Sham potential. But now we have extra potential in red. This is the Hubbard potential. This is the derivative of E of U, this Hubbard energy. And I didn't write here the expression for the potential, but it's quite simple. And in practice, we need to solve this modified Kohn-Sham equation that includes plus U correction for the D or F electrons. Okay, this was a brief reminder. Now, regarding the localized states manifold, because on the previous slide, let me go back, I showed that there are some mysterious functions phi, which are localized functions. So what are those? So those functions are the states that we want to correct. For example, in iron oxide that we saw in the lecture, Professor De Gironcoli said that d electrons are not correctly represented in LDA or GGA. So we want to correct d electrons. So those functions phi corresponds to the atomic orbitals of d electrons. And how this is implemented in Quantum Espresso, or how to tell to the code that we want to correct d electrons of iron oxide. Currently in version 6.7 of Quantum Espresso, this is hard-coded, so it cannot be provided in the input file. So this is really hard-coded in the routine called set Hubbard N and set Hubbard L. So where N stands for the principal quantum number N, like in quantum mechanics, and L is the orbital quantum number. So in the case of iron, we want to correct the 3D shell. So the principal quantum number is 3, so N is equal to 3, and the orbital quantum number is 2, because this corresponds to the d electrons. And this is coded in these two routines. In the future versions of Quantum Espresso, we plan to change this and allow to the user to specify the manifold that we want to correct from the input. This will be much better and much more user-friendly. So work is in progress. But for the time being, this is hard-coded. And if you want to modify this, you need to modify these Fortran routines and recompile the code. But we don't need typically to do that, only in some rare cases. Okay, so example 1, iron oxide. We start with the input file. You are already all experts in input for PW calculation, for the ground state calculation. So I will not discuss many things, just things related to DFT plus U calculation. So in yellow, this is what you should know already, like type of calculation NSCF. We use experimental lattice parameter. This is CLDM1. We use smearing because iron oxide comes out to be metallic. It's a fake metal at the level of LDA or GGA. So we know that it is metallic, so we need to use smearing. And we specify in this case the Marzari-Vanderbilt smearing, or it's called cold smearing. And also we need to specify the value of the broadening parameter for this type of smearing. In this case, it's 0.02 Rydberg. Typically, this is the default value, and we should use this or slightly lower. It depends on the system. And one has to carefully check this parameter. Next, okay, in blue, actually I did some explanation before. So in blue, we show the block corresponding to the magnetization. This will be described in more detail next week when you will hear about introduction to the magnetism. So here we specify n spin equals to 2, which means this is spin polarized collinear calculation. And we need to specify two parameters, starting magnetization, depending on for type 1 and for type 2. We need to specify value in the range from 0 to 1 or from 0 to -1. In this case, we just take something like 0.5 and minus 0.5. So this value can be changed, but in some cases, systems are not really sensitive to this, but in some cases, systems can be sensitive to the starting magnetization. In particular, from my knowledge in 2D materials, the solution to which you converge can depend quite a bit on this starting magnetization. So one has to check carefully, because there are many, in magnetic systems, there are many local minima. Okay, next. We have in yellow also highlighted atomic species. We have two types of iron 1 and iron 2, and we use PAW, projector augmented wave pseudopotentials. So why do we have two types of iron 1, iron 2? This is basically means that we have two sublattices. In this cartoon, they are shown in red and blue balls. So iron 1 is, for example, red, and iron 2 is blue. So we specify these two types of iron because red atoms have spin down and blue ones have spin up. So this is why we need to specify two types. Now, coming back to Hubbard specific input files. So they are actually not highlighted, but they are written here. First of all, we need to add the keyword called LDA plus U equals to true. So this is to tell to the code that we want to do DFT plus U calculation. Next, we need to specify the parameter LDA plus U kind equals to 0. This parameter can take values 0, 1, or 2. If it's equals to 0, it means we use DFT plus U simplified formulation in the Duderev framework. If you specify 1, it's more full formulation according to Liechtenstein, which can also be non-collinear, and you can have also J parameter in that case. And more recent edition in Quantum Espresso is 2, which is DFT plus U plus V, where V is the intersite correction. This was not mentioned in the lecture. I have some slide about this. I will discuss in more detail later. But for the time being, just keep in mind that we do simplified DFT plus U calculation. So we set 0. Then U projection type. This is very important point, because in DFT plus U, as I said before, we have localized functions phi. So these functions can be different. I mean, and depending on which functions you choose, the value of U also can be adapted, or I will explain, it can be computed. But basically, these functions phi are controlled by U projection type. This is the type of the Hubbard manifold, or the Hubbard projections. In Quantum Espresso, there are a few options. One is atomic, corresponding to atomic-like functions. So this corresponds to atomic orbitals read from the pseudopotentials. So in pseudopotentials, you have information about atomic orbitals of an atom of iron. So basically, we take d orbitals of iron in this case. Another option is orthoatomic. So as you can guess, ortho means orthogonalized. So what we do in that case, we take atomic orbitals of iron and we orthogonalize them between different sites, also including oxygens. And it's even possible to use Wannier functions. This is less developed for the time being, and this is work in progress. So typically we have atomic and orthoatomic options. And even though here it's written atomic, but for production purposes, it is recommended to use orthoatomic because it's, from our experience, it gives more accurate results. And finally, we need to specify the value of the Hubbard U parameter, effective Hubbard U parameter in this case. This is a trick. We essentially put it equals to 0 because we want to do PB sol calculation in this case, so without Hubbard U correction. But we put it some very small number just to activate the DFT plus U machinery, because when you use DFT plus U, the code prints extra information in the output file. So we want to see this extra information when we don't have U correction. So that's why we just activate all flags, but essentially we are not applying any U correction. So we're just trying to cheat the code. And we specify two values of Hubbard U parameters, one corresponding to iron 1 and second corresponding to iron 2. In this case, they are equal. But if you say, for example, have a system which contains different elements from the periodic table, for example, iron, nickel, cobalt, and other elements, of course, each element needs different Hubbard U correction. So you need to specify them here. But in this specific case of iron oxide, we have two types of iron, but both are iron. So if these atoms are crystallographically equivalent, the Hubbard U should be the same. But if for some reason there is some complex distortion, low symmetry, and these two types of iron become crystallographically inequivalent, then we need to apply most likely different Hubbard U parameter. And the question is how to find those parameters. It's a big problem. It was a problem until some time ago, but now we have first principles method, which allows us to compute those Hubbard parameters for any element, any material at hand. So this is no longer an issue. I will talk about this in more detail in a moment. Okay, so another interesting point is that I would like to let you know about the so-called quantum espresso input generator, because I've just discussed the input for iron oxide, and during the first 3 days you learned a lot about how to set up the input, how to choose key points, cutoffs, that you need to perform convergence tests. That was the routine maybe like 10, 20 years ago and earlier. But nowadays we want to improve and make it more automatic. So for this reason, it was created a quantum espresso input generator. The link to this tool is below. So the goal of this tool is that it provides to you a first initial guess of the input. So what you can do, you can upload a crystal structure. This can be the input file that you just prepared, but let's say you don't have a lot of experience in setting up all those parameters. So you do something that you learned, but then you want to verify if that is a good initial setup or not. You just upload it here. And this tool will provide you on the input the suggested parameters for key points, for cutoffs, pseudopotentials. Or if you don't have input file, you can upload CIF file or any other formats you can choose. Then, yeah, this is exactly the parser, the file format that you upload. Then the pseudopotentials, I will mention in the next slide. You already heard a lot about pseudopotentials, that there are norm-conserving, ultra-soft, projector augmented wave. But again, which one to choose? If you are a beginner, you can be lost and don't know what to do. But nowadays we have a standardized library. It's called SSSP. So basically, no longer a problem. You just go there and pick up pseudopotential for the element you need. Next, you need to know preferably the type of your system. Is it metallic or insulating? Is it magnetic, non-magnetic? So of course, it's not easy to tell, but maybe you know it from the literature or some other source. But you need to provide this information as an initial guess. And then you specify the density of k-point grid. So it's not the grid directly like 2 by 2 by 2 or 4 by 4 by 4, but it's rather the the distance between k points in the reciprocal space in the Brillouin zone. So in this case, for example, we want to tell that, please tell me which k-point grid I need to use in order to have the distance between nearest k points of 0.21 over angstrom. And this will give you the accuracy of 0.2 eV on the energies. And this corresponds to the fine grid. But then there are other two options which give more denser K meshes. So this can be controlled here. And of course, depending on your structure, you have different size of the unit cell. So for the small cell, you need more K points in the Brillouin zone because the Brillouin zone is larger. Instead, if your unit cell is large in real space, so the Brillouin zone will be small, so you need less K points. So with this QE input generator, it can provide you the good initial guess for the input parameters. But of course, you should verify that. You just need to still do some checks, convergence checks on K points, decrease it a little bit, increase, and see that it's really the good suggestion by the tool. And speaking of SSP library, the link is below. But again, this is very well tested pseudo potentials. So what was done, people from Lausanne, from EPFL, from the group where I work now, they took different pseudo potential libraries existing, and they compared all of them. So many properties were computed, like phonons, total energies, and many other properties. And this, for each pseudo potential, all these properties were compared with all electron calculations that do not use pseudo potentials at all. So that is a reference. And by doing this comparison, we pick up the best performing and the most accurate pseudo potentials. So if you need some pseudo potential, for example, iron, we see magenta color, and oxygen, also magenta. So actually, I don't have it on my slide, but this corresponds to some specific pseudo potential library, which is PS library generated by Andrea Del Corso using the atomic code that is included in Quantum Espresso. But if you take some other element, for example, nickel and again, oxygen. So oxygen is from one library and nickel from another library. All right, let's move on. Coming back to DFT plus U. Before we discuss the input for the SCF calculation, self-consistent field calculation, and this is the input for the NSCF, non-self-consistent calculation. We consider this input because we want to compute projected density of states. So as you learned already, first we need to do SCF calculation and then NSCF calculation. And here many things are the same, actually exactly the same as in SCF. Just in yellow, I highlight that we need to add a number of bands. In this case, it's 35. So we didn't specify this parameter in the SCF input because in the SCF, the code will compute just occupied states for insulators. And for metals, it computes occupied states plus 20% of empty states. So since iron oxide is a metal, we add smearing. So we have not only occupied states, but a little bit of empty states and partially occupied states. But here since I already checked before that I want to include a bit more that was already computed. So we add a bit more empty states. So this is why we have 35, but for each system, this should be checked, must be checked. And also here we use denser K-point grid because in the SCF, we use 3 by 3 by 3. And here we use 6 by 6 by 6 because NSCF is much cheaper, so we can use denser K-point grids. But notice that these parameters are not converged. This is just for the demonstration purposes. So of course, you need to carefully check the convergence of the calculation with respect to K points and even cutoff, of course, cutoffs, they are also very low. Okay, so SCF, NSCF, and the last point is calculation of the PDOS. This is the input file. We specify a type of smearing, Gaussian in this case, the broadening for this Gaussian function, which is in Rydberg units, not electron volts, and the energy range in which we want to plot the projected density of states, and delta E is the step. And once this is done, we will use the GNU plot script. It's called plot pdos.gp to plot the spectrum. Okay, so now let's perform calculations. Okay. So now we're back to the virtual machine. We are in day 4, example 1.dft plus u. So any questions so far? If anything, you can either unmute yourself or...
You can raise your hand also.
Yes. Okay, if not, let's move on. So, as I mentioned before, we will use HPC facilities for this exercise because it's quite heavy. In this repository in day 1, in example 1, you click on readme.md, and these are the instructions. So you can proceed on your own, and I will try to proceed as well. So we have 3 parts. One is standard DFT calculation, second DFT plus U, and third calculation of Hubbard U. So let's do the first step. Okay. Okay, let's use HPC. Now, let me remind, if you, in case you missed it or you forgot, if you click on Mozilla browser, here there is a button called how/2. Okay, you click on it, then you choose remote access usage, and you scroll down, and these are the commands: Remotempi Run to submit the calculation with the default number of cores, which is 20, and we will use remote SQ to monitor the execution of the calculation. So please do not open the output file when the job is running. So just submit the calculation and monitor the execution with remote SQ. And then we copy file to our virtual machine. So let's do that. So we type remote MPI run, then pw.x minus input, and the name of the input file. This is pw.feo iron oxide.scf.in. Okay, so the job was successfully submitted. Now let's see what's happening. We type remote_SQ, press enter. Okay, so the job is running already 10 seconds. It should be very fast calculation. This is standard DFT calculation. Still running. Okay, while waiting, there is a question on YouTube. How is the double counting correction implemented? So there are different types of double counting. And in Quantum Espresso, one of them is implemented. It's called fully localized limit. Next, missing SSP PP from different libraries. mixing pseudopotential from different libraries. Is it okay? And different norm-conserving ultrasoft PW. Yes, this is okay. You can mix pseudopotential from different libraries and even different types of pseudopotentials. You can use norm-conserving and with ultrasoft. What you cannot do is to mix functionals. For example, for iron, you use LDA, and for oxygen, you use PBE. So that is not as possible. But as long as you use one functional, you can mix pseudos. Okay, this calculation should be finished. Okay, now let's copy the file from the cluster here on the local machine. So this is done by rsync _from_HPC, and we do quotes star dot out, enter. Okay, copied files. And we have this. We can open the file, output file pw.ironoxide.scf.out. Okay, you're already familiar with the output. Let me just highlight what is new with respect to in DFT plus U with respect to DFT. So I just remind that this is DFT calculation, but we activated the DFT plus U machinery just to print some extra output, but the U correction is actually 0. So what is in particularly interesting is that at the end of the self-consistency, the DFT plus U machinery prints some information about the occupation matrix. So let me recall what is this. The occupation matrix is this object n I sigma mm prime. So this is a matrix, okay, with respect to mm prime. In the case of iron, we are considering 3D electrons. So the orbital quantum number is 2. So the size of the matrix with respect to mm prime is 5 by 5. Okay, so this is a 5 by 5 matrix. And we can compute the trace of this matrix. So take the sum of the diagonal elements, and this will give us number of electrons in this 3D shell. What we can do, we can also diagonalize this 5 by 5 matrix and obtain its eigenvalues, which can also tell us what's happening in the system. So let's see where is this. So in the output, we see the trace of the occupation matrix. This matrix is called NS. Na is the atomic index. So we take the trace of this 5 by 5 matrix, and we have for the spin up, for the spin down contribution, and the total, which is spin ups plus spin down. For the spin up, we see we have 4.98. So this is the number of electrons in the spin up channel of the 3D electrons of iron. And this is number of electrons, which is 1.8 in the spin down channel for the d electrons of iron. And if you take the sum, you get 6.78 electrons overall in the 3D shell. So we know that roughly almost 7 electrons on the 3D shell, not exactly 7, but around 7. But this is not a very accurate estimate because we used atomic projectors. So it's better to use orthoatomic projectors, which will give more physically meaningful value for the number of electrons. And you can compare, you can determine the oxidation state of iron oxide. I mean, since oxygen is 2-, so iron is 2+. So you can count electrons and see what you should expect. So for atom 1, this is information about number of electrons, spin up, spin down channel, the total, and these are the eigenvalues. This is what I said before. When you diagonalize the 5 by 5 matrix, you obtain 5 eigenvalues. So on the diagonal, you have 5 eigenvalues. So we see that all of them are almost 1, so which are fully occupied. And also you have eigenvectors. And so this is for the spin 1, which is spin up. And for spin 2, which is spin down, you see that in the spin down channel, instead of 1, we have some fractional occupation. So we see that those are partially occupied. So when it's 1, it's fully occupied. When it's 0, it's fully empty. So here we have partial occupancy in the spin down channel. And then for the second atom, because we have second iron, we have the same information, number of electrons. It's actually reversed. So in the spin up channel, we have 1.8, in the spin down 4.98, but the sum is the same, 6.7 as before. And now again, here we have some reversed picture. So in this spin 1, we have fractional occupancies, in the spin down, fully occupied. Okay, now let's continue. Now we do the NSCF calculation. Same way. So we do Remotempi Run PW.x, read the input. Now we add NSCF and we execute. Okay, let's check if it runs properly. Yes, it works. Okay, still running. Okay, one question by colleague of mine, Nikita, about we can see LDA plus U parameters, but pseudo-potentials are PB sol. Is it okay? Yes, we are using PB sol functional because this is three-dimensional crystal. So for bulk systems, we should use PB sol GGA functional. Why PBE? So because PB sol, I mean, sol stands for solids. So PB sol was optimized for solids, while PBE, that was optimized for molecules. So PBE should be, well, historically PBE was created before PB sol. That's why people applied also PBE in solids, but PB sol is now developed, so we should use PB sol for solids.
Iurii, we have also one raised hand.
Yeah.
Will you want to answer now or?
Yeah, yes, now it's okay.
Okay, so let me activate micro. Yes, please, Samira. Now you should be enabled.
Good morning, sir. Please, why did you do this step remote in the beginning and now? This is my question.
Sorry, what?
Yeah, the audio was not very smooth. Could you please tell it again, maybe slower and don't speak too close to the microphone, maybe?
Yes, sir. Good morning and sorry for the interruption. My question is, why did you write remote in the terminal in the beginning?
I didn't get the question. Ivan, did you understand?
Why did you something in the terminal at the beginning? I didn't get just the middle word.
The command remote.
Remote.
Remote. Oh, okay. No, thank you. Now it's clear.
Okay. So this is okay. Remote_mpi run. So this is the special command created for this school because we are using the cluster. So when we execute this command, what happens underneath is that the calculation is submitted in the cluster. So not on your computer, so via SSH, the message is passed to the cluster, one of three clusters that we use. And there are local scripts on the cluster which are submitted and the calculation is run there. So, I mean, if you're connected directly to the cluster, you're using MPI run or other analogs on the HPCs. But here we have a special command for this school, which does more than just that. It simplifies our life a lot. So just with this simple command, you submit calculation. That's it. So this was explained yesterday. All right.
Thank you, Samira, and thank you, Iurii, of course. We have questions from streaming. Do you want me to read them, or you read yourself from the chat?
Let's. No, please. Let's answer one more, and then maybe we answer others later. Okay.
So the first one from streaming is mixing SSSP pseudopotential from different libraries. Is it okay? Or if different non-conserving PAW on Ultrasoft?
Yeah. This actually I already answered. It's possible to mix it. Yeah.
Okay. The next one is how is the double counting correction implemented?
Also answered. Fully localized limit. Maybe the last ones.
How we can read the eigenvectors for each eigenvalue by row or column? This is
okay.
And the last one, how should I give FE1, FE2 for inequivalent atoms? And the last one, what difficulties can NBE calculation have in magnetic systems applied DFT plus U?
Okay, regarding the eigenvectors, I mean, I never really used that information about eigenvectors. And that's why I cannot answer, is it by row or by column? But this can be easily verified by checking the code. So I will check this and I will answer on Slack. Okay, so this I will answer later. Next.
Yeah, maybe Iurii, because the guy who posted this question is on YouTube streaming.
Oh yeah, so I will.
So he cannot get the answer by Slack. So maybe
yes.
We can answer later on during the hands-on, or maybe even in tomorrow or on voice, because.
Yeah, I know the name of the routine. I mean, if you're familiar with Fortran, you can check. So I write on YouTube pw/src/write_ns.f90 to check.
So pw/src
write_ns.
Write_ns.
Yeah, there you can see how it's printed.
.f90, right?
Yep.
Okay, so I have just written in the YouTube stream channel, so you can check there.
Yeah. Okay, next question. Should I give iron 1, iron 2 for inequivalent atoms? Yes, so in this case, we use iron 1, iron 2 because of spin, because we want to have one spin up, spin down, but these are still equivalent. If it happens that we have just 2 iron in our simulation cell, but if you take some other polymorph of iron oxide, which has bigger cell, so you have more than 2 iron atoms, it can happen that not only you need to define 2 types of iron because of spin, but it can happen that even there are some crystallographic inequivalence between irons. So you can define maybe more types of iron. So by playing this trick of different types of iron, you can control spin and also inequivalence between atoms. So you can have iron 1, iron 2, iron 3, iron 4. First 2 correspond to spin up, spin down, they're equivalent, and iron 3, iron 4 also spin up, spin down, but they are another set of inequivalent atoms. And last question, what difficulties what is NBE? Can be calculations?
Maybe they mean a NEB, N-E-B.
NEB.
I guess, I don't know.
Sorry, I don't understand that question.
So maybe William Selin, maybe you could repost the question on the YouTube stream. Yeah, it's
Okay, there is also a question, PBSOL is better for 2D materials than PBE. So in our group, we use PBE for 2D materials because PBE is for, let's say, molecules, PBSOL for solids. 2D is in between. So there is a question, is it PBE or PBSOL? Well, from my knowledge, people use typically PBE, but you should compare PBE and PBSOL just to be safe. Okay, and Stefano answered, eigenvectors are by column from lowest to highest, the same ordered the eigenvalues. Okay, thank you. Okay, just to move on because I'm super late. So we did SCF and NSCF. Now the last step is calculation of the PDOS. So we type Remotempi Run. It's called projwfc.x minus input, and we type the name of the input file, which is projwfc iron oxide input. Submit. Remote SQ. It's already finished. Yes, takes a few seconds. Now we need to copy files. Let's do this way: rsync from HPC dot. So we copy everything because I don't remember the names of files, and there are many actually. So this should copy all files from the cluster to my local machine. So we see that the PDOS calculation produced many files, each of them corresponding to specific type of orbitals. So for example, these S electrons of iron, then you have P electrons of iron, D electrons of iron. So what we want to plot a figure which we saw in the lecture for iron oxide. So we want to plot D states for iron 1, D states for iron 2, and P states of oxygen, and see how this looks. So for this, we have a script. Where is it? It's called plot underscore PDOS GP. So you just type GNU plot and the name of the script. So let's do that. GNU plot, the name of the script. Okay. So this produced file called iron oxide underscore PDOS. Oops. Now let's visualize this. Okay, so we use this command etril. So you should obtain this. I guess many of you already obtained it half an hour ago because you're faster. But this is in fact what we saw in the lecture. So the vertical axis is the projected density of states. Horizontal axis is the energy minus Fermi energy. So our zero corresponds to the Fermi level. We see in red, iron 3D majority spin. So we have, in fact, they are fully occupied because we saw that eigenvalues are one, essentially one. So we see they are all occupied. And for the other iron minority spin in green, we see that they are around the Fermi level because we saw that eigenvalues were not one, but they were some fractional numbers between 0 and 1. And for oxygen, we have blue PDOS, which is also mainly occupied. So this is a problem of standard DFT with LDA or PBE or PBSOL. Now we want to apply the plus U correction. So to do that, sorry. So you follow, not this one. So in the extractions of this exercise, you do step 2. You add the value of the Hubbard U parameter, which is 4.6. And all the rest is the same, but you just repeat steps that you saw before. SCF and SCF, projected density of states. Okay, so, and I will not do that in the interest of time. So let's see what is the final result. Yeah, okay. So on the left is our DFT result, on the right is the DFT plus 2 result. So when we apply the Hubbard U correction, so what happens is that we apply the, we remove self-interactions for the d electrons. So they were delocalized in PB-SOL, but by putting plus U correction, we are localizing them more as they should be. And when we do the self-consistent cycle, what happens is that the calculation converges to the insulating ground state. So we have a band gap now. And in fact, this agrees with the experimental observation that iron oxide is an insulator. So this is good news. So plus U correction works. Now the question, very interesting question, and it's the main problem of the DFT plus U method. Why and how to choose the value of the Hubbard U parameter? And why did we use 4.6 electron volts? So 4.6 EV, we use just an example for demonstration purposes. But what we need to do in practice, we need to find the value of the U parameter somehow. So what many people typically do, they use empirical value by trying to reproduce, for example, the value of the band gap. For example, you know that in iron oxide, there should be band gap. I don't remember the experimental value. Let's say, I don't want to say some random number, but some value, and we want to reproduce that value as close as possible, but we can try different values of Hubbard U parameter, and we can pick up that one which gives us the best band gap. So this is what many people do. However, this is not a very satisfactory approach because, first of all, DFT plus U is not really the method for computing very accurately the band gap. DFT plus U is the method to correct the energetics of the system, to remove self-interaction and to have correct energetics of the system. Band gap is a spectral property because you need to have conduction states, so on and so forth. So trying to reproduce experimental band gap is already not really the best way to go. But the better choice is to compute Hubbard U using first principles methods. There are different methods. Professor De Gironcoli explained that there is linear response method, but there are also others like constrained random phase approximation and some other methods. So in this slide, I would like to tell a few words more about linear response. And also, as Professor De Gironcoli mentioned, recently we recast this theory or formulation in a more computationally efficient way using density functional perturbation theory that was initially developed for phonons, which will be discussed tomorrow by Professor Baroni. So DFPT was created in the late 80s. The first paper was in 1987 for phonons. Then in 1991, very extended physical review B paper by Professor Giannozzi, Professor Baroni, Stefano De Gironcoli, and Andrea Dal Corso, or maybe I'm wrong. And then there is a review paper in 2001, if I'm not wrong. But you will learn tomorrow about DFPT. This is a very powerful theory. And we use this intelligent idea also for this problem of computing Hubbard U parameter. it's quite theoretically involved, so I will not discuss here. Just say that U is defined in this way, where chi and chi naught are so-called response matrices, which can be computed by obtaining the response of our occupation matrix to some perturbation with the strength of the perturbation lambda. And in this DFPT framework, this object is defined as the sum over Q points over this complex object delta n of Q. So unfortunately, I don't have time to explain in detail, but the message to pass is that there is some Q point sampling of the Brillouin zone, and each Q points, Q vector, if you want, corresponds to the wave vector of the perturbation, so-called monochromatic perturbation. So we have several monochromatic perturbations, and for each of those perturbations, we compute the linear response of the system. By summing up all responses, we obtain the total response from which we obtain the value of Hubbard U parameter. So physically, what we do in our system, we apply some perturbation to the electronic occupations. For example, in 3D shell of iron. So we perturb slightly the electronic occupations in the 3D shell and see how the system responds to this. And from this response, we can obtain the value of the Hubbard U parameter. And how to compute it with Quantum Espresso? There is a recent code called HP, standing for Hubbard parameters, that implements this idea using density functional perturbation theory. The input is very simple. You just provide prefix and output directory if needed, and the Q point grid, which I mentioned. In this case, it's simply 1 by 1 by 1 to make it fast. But in practice, you need to converge the value of Hubbard U parameter with respect to this Q mesh. So Q mesh and also K point mesh. So U value must be converged. So so this is why we use 4.6, because if we compute Hubbard U for iron oxide using Q mesh 111 and K mesh 333, we obtain 4.6. But of course, this is not converged. So this cannot be used for production purposes, but this is just for demonstration purposes. And
Iurii, sorry, there is a question which I think is pertinent regarding the calculation of Hubbard parameter.
Yeah.
That is, if there is an easy way to determine a range for the U value. So yeah, if there is an upper bound for.
Is there any upper limit of U value? No, there is any constraint. And in fact, if this method is not suitable for closed shell systems, so when the d electrons, this shell is fully occupied, in that case, this method gives unphysically large Hubbard U parameters. It can be 20 eV, 50 eV, unphysically large. So this method is not suited for closed shell system, only for open shell systems where the electrons are partially occupied, like in iron oxide. And also, since we're talking about questions, there was a question on Slack or in Zoom, I don't remember. So because some participants says that the U parameter is applied to 6 S states in some system. And that was done using empirical U to reproduce the experimental band gap. So question was, can we apply U to S states or even to P states? So typically, U correction was introduced, as was explained, going from the Hubbard model when there is a problem of strong correlation. So historically, LDA plus U or DFT plus U was used for correcting D electrons and F electrons. But then later, people realized that actually, when you introduce the Hubbard correction in the framework of DFT, it actually cures self-interactions and not correlations. Correlation problem is very complicated problem, strong correlations. You need multi-determinant theory, and there are symmetry arguments. It's very complicated problem. So the DFT plus U is not the theory to cure strong correlations. It's really curing self-interactions. And self-interactions are present not only for D and F electrons, they're also present for P electrons and S electrons, for all types of electrons. They are larger for D and F electrons, and they are smaller for S and P. So in principle, why not applying U to P states or even S states? And in fact, in the literature, some groups apply U correction to the P states of oxygen, for example. There is no general consensus on this point, but this is what people do. But putting U on P states is, well, has to be discussed. For the S electrons, it's even more questionable. But then people do what they want. You apply to S6S, you try to reproduce experimental band gap. Yeah, I mean, don't know what to say. Yeah, so that's basically the comment. But to move on, we can compute the Hubbard U parameter. Let's do that quickly. So this is explained in point 3. You can skip the step of cleaning temporary directory. So what we need to do is to run the NSCF calculation as before, and running the HP code, hp.x, read this input. So since we're running on the cluster, we don't need to add this name of the output file. And instead of this symbol, we need to put -inp or -in. So let's do that. So we do Remotempi Run w.x -input, and the name of the input file pw.iron-oxide SCF input. Remote SQ to check. The HP calculation will be much longer than the PW calculation, because PW is the ground state calculation, while HP is the linear response calculation. It can be 20 times longer. It depends on the system, it depends on the density of the Q-point grid and other things. Okay, so SCF is finished. Now let's submit the HP calculation. So Remotempi Run hp.x, and the name of the input, it's hp.iron-oxide.in.
Sorry, Iurii, may I say, just interrupt you 1 minute? Okay, for the people that is running on the CISA cluster, please, before launching, starting jobs, remote jobs, please run the update reservation name, update CISA reservation name command, as it is in the instructions in the how-to. Because if you don't do that, you run the jobs in the queue of all the users, not in the reservation for the school. And so, first of all, you remain in queue without the job executing, and second thing, you occupy nodes that are not reserved for the school. So please, just read the instructions in the how-to remote and follow the instruction for CISA. This must be done every morning before starting the hands-on. Sorry for the interruption and the inconvenience.
Okay.
Thank you.
Okay, the calculation is finished. Let's copy it here. So we do rsync from HPC dots. Okay, and we can check the output file. Well, HP calculation will produce a file called iron oxide.Hubbard parameters.dot. So we can open it. And in this file, you see information about the Hubbard U parameter, which was computed. And we see that, in fact, for iron 1, the U value is 4.6055. And for iron 2, it's exactly the same value. So we obtain exactly the same value for two irons. And because they are crystallographically equivalent, they just differ by spin, but this doesn't mean that U should be different because of spin. There can be spin resolved Hubbard U, but this is also work in progress. For the time being, we have global U for both spins. Okay, now a couple of questions before we go to the second example about hybrid functionals.
We have Ignacio with the raised hand. Can we answer each
Yes,
question?
please.
So let me.
Thank you. So on this issue of calculating U for orbitals other than 3D and 4F, I was thinking about these projectors that you have, or these inner products between the bands and the atomic wave functions. And my question is there a problem if the wave functions that we use are actually pseudo wave functions which don't have nodes?
Okay, no, it's not a problem. So we use, in fact, pseudo wave functions. So for the Consham wave functions, we have pseudo wave functions, and we project them on the 3D atomic orbitals of iron. So no, there is no any problem there. So we don't need the information about core electrons of for the Consham wave functions, because in Consham wave functions we have just valence electrons, which make the chemistry. So we project those on 3D electrons.
But, and excuse me, if you were to project the Consham orbitals over atomic orbitals which have nodes, but you're actually approximating those with pseudo atomic orbitals that don't have nodes.
Oh, okay, yeah.
That was the question, if that could become a problem or not.
Ah, okay, sorry, yes. So we were referring to atomic orbitals. No, it's not a problem. No issue.
Okay, thank you.
You're welcome. Then other comments?
Yes, we have another from Samira.
Sir, my question is, did we need to modify the input before doing the second calculation, the calculation of a U parameter? Because when I check now the input that we have in the day 4, there isn't the value of U in the input.
Okay. Yeah, so in this example, there is a note that before running the SCF calculation, you need to initialize back Hubbard U to 10 to the power minus 8.
Yeah.
To start from the PB sol ground state. I think what you did, you forgot to do this. So I guess in your SCF input, you still have 4.6, correct?
Okay.
I think so.
I will
And
check.
so what happened is that in your test, you use 4.6. So this means actually your ground state calculation is DFT plus U. And from this ground state, you compute the Hubbard U, and it's different. And this is expected. So this is another important point that actually I was not planning to discuss, but this is important. So we need to do self-consistency when we compute Hubbard U. So what does this mean? When we compute Hubbard U from the DFT ground state, So with U equals to 0. What happens is that our ground state is completely wrong. It's metallic. And so from this completely wrong ground state, we obtain U 4.6. If we repeat this step again, we put in our SCF the value we just computed, 4.6. We redo the ground state calculation with DFT plus U, and we open a gap. So now our ground state is way better than before. Now we have insulating ground state, which is much closer to the truth. And starting from this improved ground state, we compute again the Hubbard U, and you obtain something maybe 5 or 6 EV. I don't know what did you obtain. So what we do next, we use this updated value of U and we plug it in again in the SCF calculation. So we redo again the DFT plus U ground state calculation and recompute U again. So we do this so-called cell consistency loop until Hubbard U does not change. So this way, we obtain the self-consistent value of the Hubbard U parameter. If we do just one shot, it's called one-shot calculation. You just do DFT and on top you compute U. That is not the value you should use for production purpose. You need to do it self-consistently. Moreover, there is an external loop of self-consistency for the geometry. So to go even further, what we do, we not only compute U self-consistently, we also relax, optimize our structure in the external loop. So we do this double loop for the structure and calculation of U until the value of the Hubbard U does not change and until geometry does not change. So this is very important because your Hubbard U is consistent with the geometry. And that value of U that you obtain and that geometry that you obtain should be used for the production purposes. There is a paper we published in this year in January in Physical Review B that discusses this point. So you see, DFT plus U is quite tricky when you start working on it. It's not just picking up some random U or empirical U, running calculation and publish something. It's there is a lot of details that you should be aware.
Thank you, sir. And if you can let us the title of the paper.
Yeah, I will write it on Slack and on YouTube. It's Physical Review B 2021, where I'm the first author, so you can Google it. Okay, next.
Thank you, Samira. We have 4, which might be reduced to condense to 3 questions from streaming. And another raised hand. Would you like to proceed to answer?
Yeah, the point is that we have little time. We have 15 minutes, correct? And then we have another half an hour. Can we use that half an hour?
Well, we have, yes. No, we have until 12:30.
Okay,
so yes, we have 45 minutes
okay,
left.
Okay, because DFT plus U was initially for half an hour, but now it's 1 hour and 15 minutes. Okay, so let's answer a few questions.
Just do as you want.
Sure.
If you want to.
This is my favorite topic, so I can continue forever. So then, okay, let me explain the last thing, and then again questions, and we move on.
Okay.
Because I mentioned about DFT plus U plus V. This is extended formulation, where we have not only the Hubbard U correction, which is on site. So we're correcting electronic interaction sitting on iron atom. But also we're adding another contribution, actually subtracting another contribution, which depends on the V parameter, which depends on 2 indices, I and J. And this is the so-called intersite interaction. So in the case of iron oxide, this extra contribution will correct interaction between 3d electrons on iron and 2p electrons on oxygen. So this is why it's called intersite or interatomic interactions. And in this cartoon, we see that in DFT, 3d electrons are over delocalized. in DFT plus U, we are putting plus U correction. So it's a penalty. We are localizing electrons, so they become less spread and sharper. And in DFT plus U plus V, in fact, we apply plus U to make it sharper, so to localize 3D electrons. But we also take into account the effect of ligands. We know that there are oxygens. Oh, this is not the right structure, but we know that there are oxygens around iron. So, and 2p electrons of oxygen interact with 3D electrons of iron. So we take into account that interactions and we correct that. So this extended functional gives more flexibility, and this functional allows us to correct not only the localization problem of 3D electrons, but also correct the interactions with ligand states. So this general formulation is very powerful. And from our experience, DFT plus U compared to hybrids, because some people asked if DFT plus U is better than hybrid functionals or GW. So DFT plus U is worse than hybrid. Sometimes they are quite compare well, but sometimes hybrids are superior to DFT plus U. And if you use this extended formulation, DFT plus U plus V, this extended formulation gives much closer results to hybrid functionals. But it is important to remember that we should not take hybrid functionals as a reference, because hybrid functionals are also approximate. You have a fraction of exact exchange, which is 25% in PB0 and HSE 0.6. But hybrid functionals also fail in solids because this fraction of exact exchange is not proper, not correct. So there are more advanced hybrid functionals. They're called dielectric dependent, developed in the group of Giulia Galli in Chicago and other works by Kronig and other groups. So they choose the fraction of exact exchange ab initio. So they compute it. Actually, I will discuss about this soon. But to summarize, standard hybrids like PB0, HSE 0.6, they're also not perfect for solids. And taking them as a reference is not always a good idea. But in some test cases that we considered from our experience, DFT plus U plus V is in good agreement with hybrids, or sometimes even superior. Okay, and to finish, not only U, but also V can be computed using the HP code in Quantum Espresso, using the latest version. Okay, before we move on, let's answer a few questions on this first part. Okay.
Yeah, we have two questions from streaming, which are related. We can plot the density of state of subbands, maybe subbands of d orbitals. I mean dxy, yz, zy. And another related, how can we plot dEg and the T2G states?
Okay, so for the first one, yes, we can plot different contributions. You just need to open this file. Let me try to do that. Not sure this works. Okay, so 1, and then 5. Okay, if you open this file produced in the PDOS calculation, it doesn't want to fit. So we do view, zoom out. Okay, in the PDOS file, you see lots of numbers. There are many columns. The first column is the energy. Second and third are local density of states for the up, spin up, and for the spin down. So this is what we plot actually in this example. Plot for the spin up and spin down. But if you are interested in really contributions to this local density of states, of this dxy, dyz, dzy, etc. So these are, I highlighted them. For the spin up channel, we have 5, of course, because this is the D shell. And for the spin down, we have 5 as well. Also, at the end of the PDOS output file, where is it? Should be proj output. At the end of this file, there is useful information, so-called loading charges. So for atom 1, you see lots of interesting information, and what you're asking is essentially there. So for the spin up, the electrons, you see dz squared, dxz, dyz, etc. So you see those numbers, and you can identify and plot them using the file I showed before. And regarding T2G, EG, this is not explicitly written anywhere. So, and actually I have also troubles to identify what is what. So we need to plot these contributions and analyze a little bit the results to identify where is T2G, where is EG. But you don't have something explicitly written T2G or EG in the output. But I think this information is enough to obtain what you need. And then what else?
Another one from streaming, HP.x code. Calculate Hubbard parameters for the atoms that have Hubbard parameter assigned in the SCF calculation, right? What if I wrongly assign Hubbard parameter for O in the SCF file?
So the last question, what if I wrongly assigned Hubbard parameter for oxygen? What does it mean? If you wrongly assigned, well, you will obtain wrong results. Say, maybe I didn't get the question right, but I mean, if
yeah, maybe it can be if you want to write, if you Radzi Morad, maybe write reformulate it on YouTube so Iurii can answer more precisely.
Just to comment. So, for example, for iron we put 4.6 and 4.6, and for oxygen we put Hubbard U3. So we put 3 because oxygen is type number 3 in the atomic species list, and for oxygen we put the value we compute or we want. Okay. So next, is it better to use DFT plus U plus V to evaluate D-band center? Not sure I understand the question. And don't understand what does it mean, evaluate D-band center.
So again, here maybe.
Yeah, then the question, can the Hubbard U parameter, Hubbard U value be different according to the applied pseudopotential? Yes, the Hubbard U parameter is depends on pseudopotentials, depends on the Hubbard manifold, if it's atomic or orthoatomic, depends on the oxidation state. So yeah, when you report value of the Hubbard U in your paper, always remember to report which pseudopotentials did you use, which functional, which Hubbard manifold, etc., so that people can reproduce your results. Otherwise, if you just report U equals 5 EV and that's it, that's not enough, not satisfactory. Okay, how DFT plus U is better from TBMBJ? Fortunately, I don't know. I don't have experience with that functional. Is there a way to determine the G factor of transition metals of radicals using QE? Though that is not related to this hands-on. Okay, so there is a question about hybrids, but let's discuss it in the next part.
We have also to raise the hand if you want.
So we have half an hour and we have still hybrid functionals and van der Waals. So let's continue. So actually they are shorter, so they should be 15 minutes each. Okay, so let's go to hybrid functionals, example 2. And apologies for those questions that I couldn't answer now. So presentation, hybrid functionals. Okay, this is the slide to remind what you saw in the lecture. Because in hybrid functional, there is this problem of divergence for the Q plus G when it's 0 in the summation. So there is a Q mesh in hybrid functionals. So what's the meaning of this Q mesh? In the expression for the exact exchange energy, there is a double sum over bands and K points. And that is very expensive, having this double sum over K points. So to reduce the computational cost, one of the K point sums is replaced by sum over Q points, which is has less Q points than in the original K point summation. For example, if you have a double sum of over K points, and each of these sums runs from 1 to 100. So we have 100 times 100 terms. That is a lot. So what we do, we say the following. The first K point sum we keep from 1 to 100, and the second K point summation we replace by Q points from 1 to 10, for example. So basically we are reducing the second sum over K points using this trick of Q points. Okay, so this is the meaning of Q points. And there is this singularity problem. There are different ways how to treat this singularity problem. And the one was mentioned in the lecture is the so-called GG Baldereschi. I think it was, if I'm not wrong, it was created in Lausanne in Switzerland and published in this work. So we will use this correction method to treat the divergence in this example. The input file for silicon with hybrid functionals is shown on this slide. In yellow, I highlight input parameters related to hybrid functional. What we need to specify is the keyword called input_DFT equals to the name of the hybrid functional that we want to use. In this example, we use PB0 functional, hybrid functional. So we write PB0. If you want to use B3lib, you write here B3lib and HSE respectively. It is important to notice that when you select pseudo potentials, you need to use those which are generated with the functional which is as close as possible to your hybrid functional. So this means that if you use PB0, you need to use pseudo potential generated using the PB functional. You should not use LDA functional in this case because you're using PB0. Unfortunately, nowadays we don't have pseudo potentials generated with hybrid functionals. So this is why people use pseudo potentials generated with PB or PB-solve functional or LDA. Next, we specify the Q point grid. These parameters NQX1, NQX2, NQX3. So we use just one Q point. So we write one by one by one. This is really the simplest approximation we can do, which just say there is one Q point, just gamma. Then we need to set up X gamma extrapolation to true. This means that we are taking care of this divergence singularity problem when Q goes to 0. If you set it to false, you basically don't take care of that, and it will be much slower convergence. And then EXX divergence treatment, we specify the Gigi-Baldereschi method. As was explained in the lecture, there are other methods. For example, spherical cutoff of the Coulomb potential, and there is also for anisotropic systems, so-called Wigner-Seitz truncation. So it's not spherical in all directions. It depends on the, if it's anisotropic, in one direction it's longer, in another it's shorter. So it takes into account this. Okay, but spherical cutoff and Wigner-Seitz cutoff, they are not supporting non-cubic systems, if I'm not wrong. Okay, this is just to remind that there are several types of hybrid functionals and different treatments of the divergence in the hybrid functional. Gigi-Baldereschi, spherical cutoff, and cutoff for anisotropic supercells. And if you specify none, then sets Coulomb potential simply to 0, but this is not really the best way to go unless you're using this specific type of hybrid, which is GAU-PB, which is not that popular actually. Okay, and now we need to do the exercise. We need to run a hybrid functional calculation with PB0 for bulk silicon. We need to compare the total energy using different Q-point meshes and see how the total energy converges as the size of the Q-point mesh. So I remind that we're using here simplification when we replace the one summation over key points by summation over Q points, but this is an approximation and we need to be sure that we are not making a big error there. So we need to make some convergence tests using or not using the extrapolation at the gamma point. Okay, so let's do this exercise during 10 minutes, and the remaining 15 minutes we use for van der Waals. So hybrid functional calculations are extremely expensive. Currently in Quantum Espresso, there is an efficient implementation for the case of norm-conserving pseudopotentials, and Ivan is an expert in this. He implemented very efficient recent method called ASE, correct? He's an expert, so if you have questions.
Yeah, yes. The method was proposed by Lin, and then I implemented it in Quantum Espresso. It's based on a projection of the XF exchange operator on the manifold. Yes, and this speed ups calculation by which factor, more or less? It depends on the systems. We registered up to 7. It depends on cases. If you compare with the very old previous implementation, is even an order of magnitude. Whereas in other cases, it can be 3, 4, 5, yes, but still it is significant, let's say. In fact, now it is the default method. Exactly. So thanks to Ivan, you can now run hybrid functional calculations very effectively and efficiently. Instead, for ultra-soft pseudopotentials and projector augmented wave, is this supported, your implementation even? Yes, it is supported. Yes, it is. Okay, okay. But just notice that in the case of ultra-soft and PAW pseudopotentials and hybrids, there is less, let's say, more limited support. I mean, some things you cannot do, like first of all, it's a bit quite slow, and also certain things cannot be done. I think it's like stress, forces, things like that. I don't remember by heart, but for non-conserving, there are more things you can do than you can do with ultrasoft and PAW. So I would suggest probably to try first with non-conserving, and then you can also try to explore ultrasoft and PAW. Okay, yeah, so you use a HPC for this case. Type as usual Remotempi Run.
pw.x minus input and the name of the input file, and you submit. Okay, while waiting, one important comment for hybrid functional calculations is there are some tricks. So if we go, oh, actually I should not do that. We go to pw.x input. There is parameter called, oops, apologies. ECAT-FOC. Where is it? I mean, on the virtual machine, I have some issues if I try to use some, you see, some commands. Basically, there is a parameter ECAT-FOC.
Yeah, there was there. I saw it.
Where is it?
It is the second line.
Oh, okay, thank you. Yeah. So there is parameter called ECAT-FOC. The default value is the same as ECAT-RAW. So this is for, you remember, non-conserving the potentials. ECAT-RAW is 4 times larger than the kinetic energy cutoff for the wave functions. And ultra-soft and PAW is 8 times larger. So ECAT-FOC is also like equals to ECAT-RAW by default. But you can significantly speed up the calculation by using ECAT-FOC value. For example, you can start to setting it equal to ECAT-WFC. But I think, if I'm not wrong, you should use maybe factor of 1.5 or 2 or something like that to have reasonable accuracy. So ECAT-FOC value can take values between ECAT-WFC, the minimum value, and the default one is ECAT-RAW. But just keep in mind, if it's very expensive computation, you can reduce this ECAT-FOC parameter. Okay, remote is 2. That was gamma point, so it's finished. So we need to do calculation for different Q point meshes. We don't have time to do that. That's why we just see this result. And in fact, we see that using X-gamma extrapolation true, we reach the convergence faster for small Q point meshes. So already at gamma, this dot, this point is closer to the converged value, this one, if we use gamma extrapolation technique. If you don't, you're more off with respect to the converged value. For the Q mesh 2 by 2 by 2, again, you see improvement when you use extrapolation, but let's say smaller. And then for the Q mesh 4 by 4 by 4, it becomes almost negligible. And at 8, you're already at convergence, 8, 8, 8. So that's why it's recommended to use extrapolation technique to allow us to use scarcer Q meshes. Okay, so this is it for hybrid functionals. Let's try to discuss, answer some questions if we can.
We have Fallon on call. Please.
Yes, thank you very much for your talk. I have a question concerning the ECAT-FOC. So you said that it will speed up the calculation, right? I want to know if it doesn't affect the total energy and something like that. Okay,
yeah, so it affects. So that's why you need to also check carefully the value of the ECAT-FOC. So when you reduce it to the value of ECAT-WFC, this cutoff for the wave functions, so this is the minimum value of the ECAT-FOC. But be careful, because perhaps in your system, this simplification can lead to some quite big errors in the total energy and other properties. So this is why always before production calculations, before publishing the results, as everything else, you always have to perform convergence tests and checks. So this parameter has to be used with care.
Okay, thank you.
Welcome. Okay, then from Slack, there was a question about hybrids. How can we modify the exact exchange mixing parameter in the hybrid functional? Also, can we modify the screening parameter present in the HSE functional? So the mixing parameter we can modify from the input. Don't recall the name of it. Ivan, do you remember the name of this mixing? So there is some parameter.
Screening parameter.
Okay, let me open it here. So, thank you, Pietro. So where is it?
If I'm not wrong, it's something X6, yeah.
Here it is, yeah.
Fraction,
So,
X6 fraction.
Yeah, here, this one, no? Screening parameter. This is screening parameter for HSE like hybrid functions.
Yeah, there are two questions. Exact exchange mixing parameter, I guess it is X6 fraction,
Yeah,
and the other
exactly.
one is screening.
Exactly. So apologies. Yeah. So the fraction of exact exchange is, I mean, it's called exact exchange fraction. Here it is. So we can change it. And screening parameter is specific to HSE. So since we're talking about this, I already opened some papers for dielectric dependent hybrid functionals from the Galli group. So what they said that this parameter alpha is actually related to the dielectric constant of your material. It's 1/epsilon. So, and of course, in different solids, the dielectric constant is different. But using global value of 0.25 is not always working well for all solids. So for those solids where 1/epsilon is close to 0.25, it should give quite good results. But for other solids where the dielectric function 1/epsilon infinity is quite far away from 0.25, then standard hybrids most likely will not give satisfactory results. So you can tune this fraction of exact exchange by computing it like 1/dielectric constant. You can go further and do even more advanced things. And this is done in another paper by the same group. So instead of using equation 5, where you have alpha 1/epsilon infinity, you can use more sophisticated expression in equation 7, which is then used in equation 6, which is this screened Coulomb potential. So in this expression for W, it's not simply 1/epsilon infinity. It's more complicated function where you use a complementary error function. It's sort of a modeled expression for the screened Coulomb. It has interesting properties that if you take the limit when R goes to R0 or R prime, so basically 2 points are close to each other, in this limit, it gives you simply 1/R minus R prime. But if you are going in the limit 1R minus R prime goes to infinity, it gives you 1/epsilon infinity. Basically, the first term survives in the limit when R minus R prime goes to infinity, and in a limit when R minus R prime goes to 0. So this term survives. I don't remember the details. I worked on this 5 years ago, but basically, if you take the two limits, you should reproduce the expected behavior of the screening of the Coulomb potential. But these features, I think they are not implemented in Quantum Espresso currently. But these dielectric-dependent hybrid functionals are very popular nowadays, becoming more and more popular for solids. So you can check the literature. Okay, and let's say last 15 minutes for van der Waals. But before we go, maybe one more question, if there is any.
Yes, Dorie Esteras.
Hello, thank you for your clear explanations and for answering our questions. I was thinking how to extract the Hubbard potential matrix you showed us at the beginning. Could we, can we do this using the STF matrices present in the output, or is something more? I mean the occupation matrix and the projectors.
Apologies, I didn't understand fully your question. So you're asking about occupation matrix in the output?
Yes. Can we construct the Hubbard potential, a Hamiltonian term, for example, to use it in a tie binding using this occupation matrix?
Oh, okay. I don't have experience with this, but I think something can be done, of course. But I don't have experience with doing what you suggest, using constructing tie binding Hamiltonian on top of DFT plus U results. But I think, yeah, I would say yes.
Okay, may I ask this in a Slack? Then?
Sure.
Thank you.
Thank you too. Okay, so let's move on. For van der Waals functions in graphite. So in this example, last one of this hands-on, we consider graphite because it has a layered structure. We have layers, and between these layers, we have van der Waals weak interactions. The experimental value of the interlayer distance is 3.3336 angstrom. If you try to use a standard LDA or GGA exchange correlation functional, you will not obtain satisfactory results because LDA underestimates and GGA overestimates interatomic distances. And we will compute those distances in this example. So that's why here we need to use van der Waals corrections. So how to do that with Quantum Espresso? You need to specify, there are two ways how to do that, depending on which type of Hubbard correction you use, semi-empirical or other ab initio. So you need to specify parameter input underscore DFT van der Waals /df. This is just one kind of van der Waals correction. There was a question earlier about van der Waals kernel. In earlier versions of Quantum Espresso, you need to generate the van der Waals kernel, not in this case, in others, so like RVV10, and then do the calculation. But in the latest versions of Quantum Espresso, this kernel is generated on the fly, and so you don't need to worry about that. And similarly to hybrid functionals, when you choose a pseudopotential, it must be the closest GGA because there are currently no pseudopotentials for non-local functionals. So this is why also you need to choose pseudopotentials wisely. So in the previous slide, I showed that we can activate van der Waals correction with input DFT keyword, but also you can do that using a different keyword, van der Waals underscore correction. And there are different types like Grimm D2. There are several ways you can specify it. It's known as DFT/D or Grimm/D2. Then there is Grimm D3 or DFT D3, Tkachenko-Scheffler, where these coefficients, C6 coefficients are computed from first principles, while in the first two, they are semi-empirical. And this XDM. And in this example, unfortunately, we don't have time to do it now, but you can do it after the ending of this hands-on session. What you can try to do is to perform these 7 calculations. In the first 5, you activate the van der Waals correction in different ways. The first 3 using the keyword input DFT. This is our non-local flavor. And the 4th and the 5th one are using the keyword van der Waals correction, DFTD and DFTD3. These are semi-empirical. So in the first 3 cases, it's really the functional that you are changing, because input DFT keyword controls the functional, while the 4th and the 5th one are just corrections that are done at the end of the CF calculation. So that's why we have 2 different keywords, which might be confusing for some of you. And points 6 and 7 are standard PBE and LDA calculations. And so what you need to do, using what you learned yesterday for the structural optimization, so-called VC relax, you need to do the VC relax calculation in these 7 ways. And then for the converged optimized structure, you need to determine the interlayer distances using XGRISDEN, for example. By doing so, you should obtain something like that. So the vertical axis is the interlayer distance, and the horizontal axis is the method we are using, actually the functional or correction, van der Waals correction. And the last 2 are standard PBE LDA functionals. And the height of each bar corresponds to the value of the interlayer distance in graphite. And the horizontal dashed line is the experimental value. So we can see that there are big variations depending on the correcting scheme. For example, we see the first 2 overestimated, RVV10, which is actually Stefano De Gironcoli worked on this about 10 years ago. And this is also supported in the Phonon code, which we'll discuss tomorrow. So the third is RVV10, which is, it seems to be the closest to the experimental value. And DFTD is largely underestimating it. DFTD3 is second best result. And we see, as I said before, PBE largely overestimates interlayer distance, while LDA underestimates. But we see, interestingly, that DFTD is even worse than LDA. This is quite interesting and surprising, at least to me. But notice that these results are not carefully converged, because, of course, we use scarce key-point mesh, low cutoff, etc., etc. So these results should be considered as not fully converged. So you should really converge them very well to be sure on the performance of each correcting scheme. But at least it gives you an idea that you see big variations depending on which van der Waals correction you choose. So that's why, as far as I know, there is no one single van der Waals scheme which is the best and everybody should use only that one. So what people typically do, they test several ones and see which ones perform the best for the system of interest, and they continue working with that. But please correct me if you have more experience and this was not totally correct. Okay, so I would say the remaining 5 minutes we can use to discuss, maybe answer some questions.
There is one question from streaming. What is the difference between input DFT and van der Waals score in the relaxation? And if we mention them in the same time in the input, what will happen?
Okay, So I think I already explained the difference between input DFT and van der Waals correction. Because in the first one, input DFT, you're really changing the functional, because input DFT controls the functional. We use this input DFT parameter also to specify hybrid functional. You remember we said input DFT equals PB0. So it's really the functional that you're changing. While here, 4 and 5, van der Waals correction, these are post-processing corrections. At the end of the PB calculation, you just apply some post-processing correction to your total energy and forces and stresses. Okay, yeah, so Ivan Girotto said that there are many questions on YouTube. We apologize that we cannot answer all of them.
Yes, some of them we are trying to answer. The questions we can maybe with as a short answer, we are doing it.
Okay.
If someone else has want to raise the hand for some voice question, please.
Sorry, there is also one question on Slack, or there is someone who wants to ask now on Zoom. Okay, so on Slack there is, so we use van der Waals to get the interlayer distance right. Would the van der Waals correction also affect the in-plane lattice parameters? In my experience, semi-empirical van der Waals also shrinks the in-plane lattice parameter, giving a worse result than the in-plane lattice parameters with GGA. Is that a common effect? Would it also be the case with van der Waals functionals? Actually, I don't have experience with that. Maybe Stefan De Gironcoli can answer if he's still around. Maybe if not, then we will reply later. Okay, I know it was explained, but in case of HSE functional, which pseudopotential is best to choose? So I would recommend to use pseudopotentials from the SSP library, but all of them are ultra soft and project augmented wave. However, I explained before that for hybrids, well, I would go for non-conserving first. So it's yeah, it's an interesting question. Maybe you can try to start. You can start with SSP library and try to use ultrasoft and PAW. If this is not working well, you can try norm-conserving pseudopotentials. There are 2 libraries for norm-conserving pseudopotentials that I know are very good. One is called Pseudo Dojo, developed by a Belgian group. So Pseudo Dojo. So this is a norm-conserving pseudopotential, so you can try them. And then there is another norm-conserving pseudopotential library. It's called SG15. Okay, and you can also try them out for hybrids. Next, does the ECAT-FOC parameter pseudopotential? No, sorry. Is it pseudopotential dependent ECAT-FOC parameter? The answer is no. ECAT-FOC is agnostic to pseudopotentials, so it just related to Fourier transform, so it doesn't matter. I mean, well, of course, for changing pseudopotentials, you should check ECAT-FOC, and maybe in some cases ECAT-FOC is smaller, in others it's larger. So ECAT-FOC indeed is sensitive to pseudopotentials, but it's not explicitly dependent somehow. Okay, in order to choose the best van der Waals correction that represents best the interaction between a substrate in a metallic slab. Shall I proceed like in example 3, following the best correction that brings the lattice parameter of the pure metallic material closer to the experimental value? My answer is yes. But again, you can also ask Professor De Gironcoli, maybe he has a more extended answer. I would try several flavors and see which one is the best. Same for hybrids. You have PB0, you have HSE. Well, a priori, you cannot tell which is the best. Commonly, people use HSE, but also you can try PB0 and others. So the same for GGA functionals, there is PBE, PBSOL, and tons of other functionals. Some are the most popular, but of course you can test different ones and choose the best ones for your system. Okay, so I think we should stop here. We can continue the discussion on Slack. If you still have some questions, we will try to answer all of them, or the majority of them. And yeah, thank you very much.
Thank you very much, Iurii. Thank you. So let me just say one more thing. Of course, we meet again tomorrow at 8:30 for Stefano Baroni will explain density functional perturbation theory. And another recommendation, if you don't have the last version of Zoom, you might find useful to update it because it might be that the breakout rooms might work better on the last version. So yeah,